Let's do some stoichiometry. Today we'll be talking about percent yields and limiting reactants. So I've got my problems. These are the ones I gave you in class. Stoichiometry III. I have my trusty periodic table of ions and my periodic table showing atomic masses ready to go here. I have a writing instrument. I prefer a pencil, but pen shows up better on the video. And of course, my calculator, not just any calculator, but the HP 35S scientific calculator. Okay, number one. In the reaction, beryllium plus hydrochloric acid yields beryllium chloride plus hydrogen. The theoretical yield of beryllium chloride was 10.7 grams. If the actual yield was 4.5 grams, what was the percent yield? Okay, well, percent yield, PY, is going to be the actual divided by the theoretical times 100. Now, the actual is what we get when we actually conduct an experiment and weigh the result. That's an actual, it's an experimental result. Okay? The theoretical yield is what stoichiometry always gives you. When you perform a stoichiometry, it assumes you have a perfect reaction, but there's no such thing as a perfect reaction. There's all sorts of variables that can't be accounted for. Maybe your reactants aren't that pure to begin with. We can't measure anything infinitely accurately, so that's always going to be off to some degree or another. But what stoichiometry assumes is that everything goes perfectly. So that will, the result from stoichiometry will always be your theoretical yield. So here we've done the stoichiometry already, and we found a theoretical yield of 10.7 grams. So when we actually ran the experiment, we found that there was only 4.5 grams of beryllium chloride that resulted from our experiment. So we will take the actual, which is 4.5 grams, divided by the theoretical, which is 10.7 grams. And the grams will cancel out, so we will say 4.5 and 10.7, divide that, and multiply that by 100 to turn it into percent. 42, it's like 0.1%, only, yeah, I just want two sig figs, so 42%. And there you go. So theoretical yield will be the actual result, the result that you get from actually performing weight measurement on a scale, over the theoretical yield, which is what the stoichiometry should tell you will happen, and then we times 100 to turn it into percent. Very good. Number one, done. Number two, the reaction of lithium hydroxide and potassium chloride yields lithium chloride and potassium hydroxide. Well, before we do anything, we know that anytime we do stoichiometry, we always need a balanced equation. So let us write this equation out now. Lithium hydroxide, lithium has a charge of 1, hydroxide has a charge of -1, so that is LiOH. Potassium chloride, potassium has a charge of 1, chloride has a charge of -1, that is KCl, and that yields lithium chloride. So that's just LiCl plus 1 minus 1, and potassium hydroxide, KOH. That's just your basic double replacement reaction. Hydroxide and chlorine switch places. And is that balanced? Yes, yes, and yes. We're good to go. Okay. If you begin this reaction with 20 grams of lithium hydroxide and excess potassium chloride, what is the theoretical yield of lithium chloride? Okay, so we're going to start with what we know here, which is 20.0 grams of LiOH. and we have excess potassium chloride. All that means is we have all the potassium chloride we'll possibly need, so we can expect that the reaction is going to run to completion with our full 20 grams. If we didn't have much potassium chloride, I would need to consider just how much of this would actually be used up, but that's not an issue here because we have excess potassium chloride. All right, so what is the theoretical yield? Well, the theoretical yield is just what we'll get from our stoichiometry, and so I'm asking for lithium chloride, so I will just do some stoichiometry here. So the first thing I will do is I want to convert this 20 grams of lithium hydroxide to moles of lithium hydroxide. So I will multiply that first by 1 mole, LiOH, and I'll divide that by the atomic mass of lithium hydroxide in grams. So I look at my little periodic table here. It tells me that the atomic mass of lithium is 6.94. Oxygen is 16. I'm going to add those together. And hydrogen is 1.01. Add those up. So it's 23.95 grams. So 23.95. Good. Now I'm trying to get to lithium chloride, so I need to jump my yield here. And I can do that using my mole ratios here. This tells me that 1 mole of lithium hydroxide is equivalent to 1 mole of lithium chloride. So up here I will put 1 mole of lithium chloride, and down here, that's an Li, down here I will put 1 mole of lithium hydroxide. Now, I'm asking for grams. Well, I didn't specifically ask for grams, but we're going to assume grams here. So I just want to lastly convert from moles of lithium chloride to grams of lithium chloride. So here I will put 1 mole, LiCl, and up top here I'm going to put grams of lithium chloride. But what is the atomic mass of lithium chloride in grams? Well, lithium, as we know, is 6.94. Chlorine is 35.45. Add those together, 42.39. 42.39. So let me just check my units. Grams of lithium hydroxide cancels out. Moles of lithium hydroxide cancels out. Moles of lithium chloride cancels out. I'm just left with grams of lithium chloride, which is what I'm looking for. So that is, I need to do the calculation. I almost wrote it. Okay. So that's going to be 23.95 divide, and 42.39 times. That comes out to 35.39. I should have 3 sig figs. So 35.4 grams lithium chloride. So that is the theoretical yield of lithium chloride. Now, we ran through this and we only produced 6 grams of lithium chloride. What is your percent yield? Well, you can see right away that that's a pretty terrible yield, right? 100% yield would be 35.4 grams of lithium chloride. We only got 6, so that's rather a dismal experiment, isn't it? But let's find out. So the percent yield is equal to the actual, which is 6.0, over the theoretical, which we just found was 35.4 grams. And that is going to be 6, enter, 35.4 divide. That comes out to 1.0 times 100. Comes out to 16.9. I just want 2 sig figs. We'll just say 17%. Very dismal result, but sometimes that's how it goes. So number 2, done. Number 3. Given the following equation, C3H8, that is propane, plus oxygen yields carbon dioxide and water. If you start with 5 grams of propane and XX oxygen, what is the theoretical yield of water? Okay, so we'll just do some straight stoichiometry. We already have our balanced equation. That's handy. So I'll just start with 5.00 grams C3H8. And I will begin by converting that to moles. So 1 mole C3H8. What is the atomic mass of propane? Well, the atomic mass of carbon is 12.01. I have 3 of those. That's 12.01. I have 3 of those, so that's 36.03. The atomic mass of hydrogen is 1.01. I have 8 of those for 8.08 for a grand total of 44.11. 44.11 grams C3H8. Okay, I'm trying to get to water, so I need to cross over here. So I'm going to go from propane to water. This tells me that the mole ratio is 1 mole of propane will give me 4 moles of water. So 4 moles H2O to 1 mole C3H8. And lastly, I'm looking for the yield in grams. So I want to convert 4 moles of water to grams of water. So down below here, I'll put 1 mole of H2O. And at the top here, I put the mass in grams of H2O. And that is 16 plus 2.02 or 18.02. That's one you probably have memorized by now because it comes up so often. So let me just check my units. I have grams of propane, cancels with grams. Moles of propane, cancels with moles. Moles of water, cancels with moles of water. I'm just left with grams of water, which is what I want. So let's do the calculation. 5, enter 44.11, divide 4 times 18.02 times. Looks like it's going to be 8.17. I should have 3 sig figs, so 8.17. grams of water. Okay, now this says that you got a percent yield of 75%. How many grams of water did you actually produce? Oh, okay. Well, you will recall that percent yield is equal to the actual divided by the I'm going to misspell theoretical. Theoretical, there we go, times 100. So this time I know what my theoretical is, that's that. I know what my percent yield is. So what I'm first going to do is just going to solve this for what I'm going to find, which is the actual. So the actual amount, which is what I'm trying to find, what this question's asking for, should be equal to the percent yield times the theoretical divided by 100. All right, so the percent yield is 75. The theoretical is 8.17 all over 100. And what does that give us now? I do wonder indeed. There's my 8.17 still in there from before. So I'll just take that 75 divided by 0.75. 0.75 times. Looks like I should have 2 sig figs. So 6.12 is just 6.1. Yeah, 6.1 grams. 0.1 grams, and that is grams of H2. 6.1. Yep, good. All right. Excellent. Number 3. Done. Number 4. We're halfway through. Halfway through. The reaction of powdered aluminum and iron 3 oxide forms aluminum oxide and iron and produces so much heat the iron that forms is molten. Because of this, railroads use the reaction to provide molten steel to weld steel rails together when laying track. Suppose that in one batch of reactants, 4.20 moles of aluminum was mixed with 1.75 moles of iron 3 oxide. What was the limiting reagent? Well, before we can do anything with stoichiometry, we need to have a balanced equation. So this is telling me that aluminum plus iron 3 oxide, Fe2O3, yields, let's see, aluminum oxide. Now, aluminum has a charge of 3, oxide has a charge of 2, -2. So aluminum, it's going to be Al2O3, that's aluminum oxide, and iron, that's just Fe. Now, am I balanced? No. You can see I have 1 aluminum and 2 aluminums, so I will put a 2 right there. And I have 2 irons and 1 iron, so I will put a 2 right there. And I have oxygen and oxygen. Everything looks good. Okay. Now, which reactant was the limiting reagent? Let's see here. This is the first problem that we have to really consider how much of each reactant we have, because that will determine how much of a product we get. So here we're given that we have 4.20 moles of aluminum and 1.75 moles of Fe2O3. So there are several ways to find the limiting reagent. You can convert it to moles and divide by the mole fraction out there, but that's tricky sometimes because it depends on what the mole factors are. That can be a little misleading. So you can take each of these and pick either one of the aluminum oxide or the iron and do stoichiometry, starting with the amount aluminum, see how much iron you get. Use this, see how much iron you get. And whichever one gives you the least amount of iron would be limiting. But to me, the method I teach I believe is the best way, because it's usually will just involve one calculation. So it's economical, and it tells us the limiting reagent right there. No muss, no fuss, and I don't have to worry about, well, okay, I have 2 moles of this. I only have, but I have 2. Okay, forget all that. So what we're just going to do, we're just going to do stoichiometry and compare our reactants. So I'll start with my aluminum here. 4.20 moles of aluminum. And I want to see, using stoichiometry, how many moles of iron 3 oxide this will require. So I will just use my mole ratios, which tells me that 2 moles of aluminum is equivalent to 1 mole of Fe2O3. Alrighty, so the moles of aluminum cancel out. I'm just left with 4.20 times a half, which is going to be 2.10. 2.10 moles of Fe2O3. Okay, so this is all the information I need. This tells me that if I start with 4.20 moles of aluminum, to use that up in a complete reaction, I will need 2.10 moles of iron oxide. But I don't have 2.10 moles of iron oxide, do I? I only have 1.75. So the iron 3 oxide is what's going to limit this reaction. I don't have enough. Now, let's say you went the other way around and you started with 2.10 moles and converted that to, you started with, 1.75 moles of iron 3 oxide and found out how much aluminum that would require. you get the same result. You would just see that it gives me less aluminum than I actually have. So just pick your two reactants and use one and find out how much you should get of the other one, and then compare that to how much you actually have. So in this case, 4.20 moles of aluminum would require 2.10 moles of iron 3 oxide. I only have 1.75 moles, so clearly iron 3 oxide is limiting. Fe2O3 is limiting. All right. Now, that's important because if I want to find out anything about my products, I know that the amount of products I have will be directly determined by how much of my limiting reagent I have. So now that I know that this is limiting, I will use this 1.75 moles in all further calculations. Here it's saying calculate the mass of iron in grams that can be formed from this mixture of reactants. All right, so I'm trying to find iron. I know I now must start with 1.75 moles of iron 3 oxide. So 1.75 moles Fe2O3. I'm trying to get to iron, so I don't need to do any conversions to atomic mass here because it's already in moles, which is what I want. So this balanced equation tells me that 2 moles of iron is equivalent to 1 mole of Fe2O3. And if I wanted my answer in moles of iron, I'd stop there, but it specifically says in grams, so I've got to do one more calculation and convert moles of iron to grams of iron. So 1 mole of iron, and the atomic mass of iron is 55.85, so 55.85 grams of iron. All right, so let's do some calculating. 1.75 2 times 55.85 times, that comes out to 195.475. I should have 3 sig figs. Okay, so now here we go. Let's look at this sig figs business. The answer is 195. Now, it can be awkward sometimes if I just write 195, even though that is clearly indicative of the number of sig figs I have. You kind of want to put a period after that, a decimal, just to show that that's my sig figs. So a better way to do that is just to write your answers in scientific notation. So instead of just putting 195 grams of Fe, a preferred answer might be 1.95 times 10 to the 2 grams of Fe. A lot of that will depend on what your teacher likes to see you do. So in this case, if I'm your teacher, let's go this route this time. Okay, problem 4. Done. Problem 5. The rare earth metal terbium is produced from terbium 3 fluoride and calcium metal by a single replacement reaction that yields calcium fluoride and terbium. Okay, as is always the case, I need a balanced equation. So let's do that first. So terbium 3 fluoride, the charge on fluoride is -1, so terbium 3 fluoride would just be TBF3. There we go. And calcium is just, of course, Ca. And that yields, it's a single replacement reaction. Okay, so the fluorine just moves from the terbium to the calcium. So this will give me calcium fluoride. The charge on calcium is 2. So this is going to be CaF2. And just good old-fashioned terbium. So there is my skeleton equation. Let us see if it is balanced. It is certainly not. Okay, the fluorines are the problem here. That's 2 and that's 3. That means I will need to put a 2 here and a 3 there. Now my fluorines are 6 apiece, but I put a 3 there, so I need a 3 for the calcium and a 2 for the terbium. All right, there's my balanced equation. There we go. Given 27.5 grams of terbium fluoride and 6.96 grams of calcium, what is the limiting reagent, and how many grams of terbium could be produced? Again, there's different methods. You look in different books, you're going to see different methods. But all of them at some point revolve around us converting these masses to moles. One thing you should not do, you mustn't do, is when you're trying to figure out what the limiting reagent is assuming because I have less mass, I have fewer grams of some reactant, that must be limiting. Granted, often that will be the case, but certainly not always. But one thing I can definitely say for sure, the one I have the least amount of moles of is indeed the limiting reactant. But again, if we just compare terbium fluoride with calcium in just one straight stoichiometry, we can get all the answers we need right there. No muss, no fuss. So in this case, I'm going to compare, I could go with calcium, compare calcium to terbium fluoride or terbium fluoride to calcium, 6 to 1, half a dozen the other. I think what I will do is I'm going to compare calcium this time to terbium fluoride. Rather than go that way, I'll go that way. That's right. I'm living on the edge. So I'm going to start with my 6.96 grams of calcium. And of course, I convert that to moles. So 1 mole of calcium. The atomic mass of calcium is 40.08. 40.08 grams of calcium. And I use my mole ratios up here. I'm going to go from calcium to terbium fluoride. So I will say that is 3 moles of calcium to 2 moles of terbium-3 fluoride. All right, but I'm only given my terbium fluoride in grams, so I need to convert this to grams so I can compare it to the amount I actually have. So one more step here, finding the atomic mass of terbium fluoride. So this is going to be 1 mole of terbium-3 fluoride. And up top now, I need the mass of terbium fluoride. So terbium, that's element 65. Its atomic mass is 158.93, 158.93. Fluorine is number 9, 19.00, 19.00. But I have 3 of them. So multiply that by 3. And then add that to the 158.93, 215.93. 215.93 grams of terbium-3 fluoride. All right, so now let's do some math. So I have 6.96, 40.08 divide. I have 2 times 3 divide, and then 250, I already have that up there, so I just multiply that, kaboom. I have 24.997, I should have 3 sig figs, so that's going to come out to be 25.0. 25.0 grams terbium fluoride. So now, is that enough information to determine my limiting reagent? Yes, it is. You can see here that the calcium, 6.96 grams of calcium, would require 25.0 grams of terbium fluoride to completely react. And I have 27.5 grams of terbium fluoride. So that means I'm going to have some of this left over. So that means the calcium is what's going to limit this reaction, the amount of calcium I have. So calcium is limiting. And there we go. Splendid. So how many grams of the excess reactant is left over? Oh, well, was fortunate. Running this equation, this experiment, using my 6.96 grams, I will use up 25.0 grams of terbium 3 fluoride. And I have 27, so 27.5 grams of terbium 3 fluoride. Because calcium is limiting, I will only use up 25.0 grams of terbium 3 fluoride. So to find out how much of the terbium 3 fluoride is left, I just take how much I started with minus how much got used up. And that, of course, is going to be 2.5 grams of terbium fluoride. Now you're thinking, wait, Mr. Bird, shouldn't you have 3 sig figs? No, because remember, sig figs behave differently when we're adding and subtracting as compared to when we're multiplying or dividing. When I'm adding or subtracting, I just need to make sure I have a number of accuracy past the decimal place that matches the least accurate number that I'm adding or subtracting. Both of these numbers just have one number after decimal place, so my answer should just have one number after the decimal place. So how much of the excess reactant is left over? 2.5 grams of terbium fluoride. Splendid. Number 5 is done. Number 6. Ammonium nitrate reacts with sodium phosphate to produce ammonium phosphate and sodium nitrate. If you start with 30 grams of ammonium nitrate and 50 grams of sodium phosphate, what is the limiting reagent? Well, to find the limiting reagent, of course, to do any stoichiometry, I first need a balanced equation. So ammonium nitrate. Ammonium, you will recall, is NH4. It has it's a cation that's polyatomic, and it has a charge of 1. Nitrate, NO3, has a charge of -1. So ammonium nitrate will be NH4 NO3. All right. Now, let me think here. Reacts with sodium phosphate. So sodium phosphate. Sodium is Na. It has a charge of 1. Phosphate is PO4 with a charge of -2. So sodium phosphate will be Na. It's 2. Hang on, let me check. Phosphate. Good thing I checked. Phosphate has a charge of -3. So it's going to be Na3PO4. And that produces ammonium phosphate. So that's NH4 3PO4 and sodium nitrate plus NaNO3. There we go. Now I just need to balance it, as they say. So let's see. I'm not going to break these up into nitrogens and hydrogens because you can see that ammonium appears together both on the left and the right, as does the phosphate. So I would treat, and the nitrate for that matter. So I would just treat each of these collectively. I'm not going to look at phosphorus and oxygen and sodium and nitrogen and oxygen. I'm just going to look at phosphates, nitrates, and ammoniums. And you can see here that I have 3 ammoniums over here and only 1 ammonium here. So it would seem I need at least put a 3 right there. So now my ammoniums are good. I have 3 ammoniums and 3 ammoniums. Let's look at my phosphates. I have 1 phosphate and 1 phosphate. And I have 3 nitrates and 3 sodiums. All right, good. So if I put a 3 there, that should work. So I have 3 sodiums, 3 sodiums, 3 nitrates, 3 nitrates, 3 ammoniums, 3 ammoniums, 1 phosphate, 1 phosphate. Okay, good. What is the limiting reagent? Now, if we just look at, well, I have 30 grams of ammonium nitrate and 50 grams of sodium phosphate. Again, can we assume that the 30 grams of ammonium nitrate is limiting? Because, heck, we only have 30 grams of it. Well, No, you shouldn't make that assumption. So we're going to do some stoichiometry to find that out. And the stoichiometry that we will do is simply to compare the amount of ammonium nitrate I have with the amount of sodium phosphate I have. So I will start here with my ammonium nitrate. I have 30 grams, so 30.0 grams NH4NO3. I'm going to convert that to moles. So 1 mole of NH4NO3. And what the heck is the atomic mass of NH4NO3? Well, I have nitrogen at 14.01, and I have 2 nitrogens, so 2 times that. I have hydrogen, 4 of them at 1.01, so that's 4.04. I can add that. And I have 3 oxygens at 16 apiece, that's 48. Add that, 80.06 grams. NH4NO3. And I want to compare this to my other reactant, which is the sodium phosphate. And this tells me that 3 moles of NH4NO3 is equivalent to 1 mole of Na3PO4. And since I'm working with grams here, I need to take one more step and convert this to grams. So down below here, 1 mole of Na3PO4 is how many grams? Well, let's figure it out. Sodium is 22.99, but I have 3 of them, so multiply that by 3. Phosphorus is 30.97. I can add that. And 4 oxygens at 16 apiece is 64. Add that. 163.94 grams Na3PO4. Now, nothing left to do but the arithmetic. So, I have 30.0, 80.06, divide that, 3, divide that, 163.94 times that. So that's 20.477. I should have 3 sig figs, so that should be 20.5. 0.5 grams of sodium phosphate. So, is that enough to determine what is limiting? Well, certainly it is, because this tells me that 30 grams of ammonium nitrate only would require 20.5 grams of sodium phosphate to run through completion. So this is excess and this is limiting. So my NH4O3 is limiting. So ammonium nitrate is limiting. So what is the maximum amount of each product that can be produced? Okay, well now that I know that this is limiting, I will use this value to start all further calculations. So I'm trying to find each of those products. So let me start with my 30.0 grams of NH4NO3. Now this part of my equation is already done for me. I've already got that here. I know that 1 mole of NH4NO3 is equivalent to 80.06 grams NH4NO3. And I know I'm just going to write the same thing down here because I'll use the same starting calculation for my other stoichiometry, so might as well. 1 mole NH4NO3, 80.06 grams NH4NO3 NO3. Now this one, I'm going to go to sodium phosphate. So this tells me that 3 moles of NH4NO3 is equivalent to 1 mole of NH4, NH3PO4, and NH4-3PO4, NH4-3PO4. And finally, I want to convert that to grams. So 1 mole of NH4-3PO4. What is the atomic mass of sodium phosphate? Who the heck knows? Well, I know that nitrogen is 14.01. I have 3 of those, so multiply that by 3. Looks like I have H4 times 3, that's 12 hydrogens, so 1.01 times 12, that's 12.12, so I take my 42.03 and add the 12.12, all right. I have 1 phosphorus at 30.97, and I have 4 oxygens at 64. I come up with 149.12. 149.12 grams of NH4 3PO4. Ran a little room there. Okay, so let's do the calculation here. 30.0, enter. 80.06, divide. 3, divide. That number actually will be the same for the next one. And 149.12 times. So I get 18.62. I should have 3 sig figs, so that is 18.6. 18.6 grams NH4-3PO4. Now down here for this one, I will find out how much sodium nitrate I have. So once again, 3 moles NH4NO3. Okay, 3 moles of sodium nitrate. 3 moles of NaNO3. And I need to convert that to grams. So 1 mole NaNO3. Okay, so sodium is 22.99, 22.99. Nitrogen is 14.01. And 3 oxygens is 48. So 85.00 grams NaNO3. And if I do the math, 30, 80.06, divide. That's a wash, 3/3. So 85 times comes out to 31.85. I should have 3 sig figs, so that comes out to 31.9 grams of NaNO3. And part C, how much of the non-limiting reagent is left over? How much is the excess reagent left over? Well, I know that the excess reagent is my sodium phosphate, and I had 50 grams of it, so I will take that 50 grams of sodium phosphate, Na3PO4, and subtract the amount that would have been used up with 30 grams of ammonium nitrate, which is 20.5 grams of Na3PO4. And that equals 50 minus 20.5. I should be able to do that in my head. What is that? 29.5? Yeah, 29.5. 29.5 grams Ma3PO4. There we go. Limiting 18.6 grams of sodium phosphate, or ammonium phosphate, 31.9 grams of sodium nitrate, and I would have 29.5 grams of sodium phosphate left over. Whew. Problem 6, done. Problem 7. Okay, another one of these. The reaction of calcium carbonate and iron 3 phosphate yields calcium phosphate and iron 3 carbonate. If you start with 100 grams of calcium carbonate and 45 grams of iron 3 phosphate, what is the limiting reagent? Well, as always, I need to have a balanced equation. So, calcium carbonate. Carbonate is CO3, and I believe it just has a charge of -1. Let me double check. Carbonate, oh no, 2. Oh dear. Yeah, 2. Okay, well, calcium has a charge of 2. Okay, so calcium carbonate, CaCO3. There we go. Iron 3 phosphate. Phosphate has a charge of 3, and iron, of course, has a charge of 3, and iron 3 phosphate. So that will just be FePO4. And that yields calcium phosphate. Calcium has a charge of 2. Phosphate has a charge of -3. So that should be Ca3PO4, 2. And iron 3 carbonate. Well, carbonate has a charge of -2. Iron has a charge of 3. So that's going to be Fe2CO3, 3. Charge 2, 6, and 6. Yeah, that's good. Okay, got it. All right. Is it balanced? Of course it's not. So I've got 3 calciums in 1 calcium, so let me put a 3 right here. I've got 3 carbonates now, and I have 3 carbonates. Excellent. Haha. I have 2 irons, but only 1 iron, so I need at least a 2 there. But that gives me 2 phosphates, and lo and behold, I have 2 phosphates. Done, bada boom, bada bang. What is the limiting reagent? Well, as always now, to calculate my limiting reagent, I will just compare my 2 reactants using a stoichiometry. And in this case, I'm going to go ahead and start with my calcium carbonate. 100 grams, 45 grams. It would seem that the iron 3 phosphate is going to be limiting, right? I only have 45 grams of it. So let's see. Let's double check, though, because we can't assume by comparing masses. We must compare moles, and that's what stoichiometry will do for us. So starting with my calcium carbonate, I have 100.0 grams CaCO3. And of course I want to start by converting that to moles. So 1 mole of CaCO3 to grams of CaCO3. What the heck is the atomic mass of calcium carbonate? Calcium is 40.08. Carbon is 12.01. I can add those 2 together. And 3 oxygens is 48. So 100.09. All right. And I'm trying to get to iron 3 phosphate. So my balance equation tells me that 3 moles of calcium carbonate is equivalent to 2 moles of iron 3 phosphate. And I want to compare the amount I have in grams, so I need to convert this to grams of iron 3 phosphate. So 1 mole of iron 3 phosphate. What is the atomic mass of iron 3 phosphate? Okay, iron is 55.85. phosphorus is 30.97. Oh, 97. And I can just add those together. And 4 oxygens is 64. So 150.82. 150.82 grams FePO4. All right, let's do the math here. So I have 100.0 grams, okay, 100.09 divide 2 times 3 divide 150.82 times, that comes out to 100 point well, I have 4 sig figs, so 100.5 grams of FePO4. All right, so what's limiting here? Well, let's see. Oh yeah, well, clearly that's limiting, right? Because to use up 100 grams of calcium carbonate, I would need 100.5 grams of iron 3 phosphate. I only have 45.0 grams of iron 3 phosphate, so iron 3 phosphate is limiting, which means for B, where I calculate the maximum amount of each product that can be produced, I must start with my limiting reactant, which is 45.0 grams of iron 3 phosphate. So 45.0 grams of FePO4. Convert that to moles. 1 mole FePO4. Already know what the atomic mass is from the previous calculation. 150.82 grams FePO4 times, I'm going to use, I'll find this one first, the calcium phosphate. So this tells me that 2 moles of FePO4 is equivalent to 1 mole of Ca3PO4 2. Okay. And finally, I want to convert that to grams. So down below here, 1 mole Ca3PO4 2. And up top here, I need the atomic mass of Ca3PO4 2. Okay. Atomic mass of calcium is 40.08. I have 3 of them. Multiply that by 3. I have phosphorus at 30.97, but I have 2 of them. So 2 times that. And I can add those 2 together. And I have 8 oxygens. 16, that's 128. Let me just double check. 8 times 128 plus, that comes out to 310.18. 310.18 grams Ca3PO4 2. All right, let's do the math. 45, 150.82 divide 2 divide 310.18 times. That is 46.27. I have 3 sig figs, so that should be 46.3. 46.3 grams Ca3PO4 2. There we go. Okay, now to find that. Again, I start with my limiting reactant, which is 45.0 grams FePO4 times 1 mole FePO4 over 150.82 grams FePO4 times 2 moles FePO4. All that's just the same from my previous calculation. And go back here, it looks like that's 1 mole of Fe2CO3. And I have 1 mole of Fe2CO3. And I need to figure out now what the atomic mass of Fe2CO3 is. So Fe 55.85. I have 2 of those. Carbon is 12.01. I have 3 of those. Boom. Can add those together. Pow! I have O3, but 3 of them, that's 9 oxygens. Pow! 291.73 grams Fe2CO3. All right, do the math. 45, enter, 150.82, that is divide. 2 divide 291.73 times. I have 3 sig figs, 43.52, so it's going to, whoops, going to come to 43.5 grams Fe2 CO3. Okay. How much of the non-limiting reagent is left over? Okay. Well, all right. Sadly, up here, when see, I went this direction. I went from calcium carbonate to iron phosphate, iron 3 phosphate. So I don't know how much calcium carbonate was used up. So I've got to do a calculation going in. Had I guessed right up here and done it the other way around, I would have been better off. And I should have made that guess because it seemed like a pretty good guess that FePO4. So I should have started with what I thought was the limiting one, but I didn't. No problem. No problem. We just do the math. So I know that I had 100.0 grams of calcium carbonate to start off with. And I'm going to subtract from that the amount of calcium carbonate that would have been used up with 45 grams of iron 3 phosphate. So in my brackets here, I will do another stoichiometry. 45.0 grams of FePO4 times 1 mole FePO4. And I know the atomic mass of FePO4 is 150.82. Grams FePO4. And that's going to be 2 moles FePO4. Oh, and 3 moles of CaCO3. And finally, 1 mole CaCO3. The atomic mass of CaCO3, I already figured that out somewhere, 100.09. 100.09 grams CaCO3. Close bracket equals. Okay. So, I'm going to start here. 45, 150.82 divide 3 times 2 divide 100.09 times. That comes out to 44.79. And I'm going to take 100, swap those around, and subtract that. That comes out to 55.2. I should have 3 sig figs, 55.2 grams. CaCO3 left over after that reaction. I should point out, depending how closely you're following along with me, you might have to do this calculation differently, starting here and actually using your parentheses on your calculator. The mode I'm in here doesn't use parentheses, so that's why I started here, if that seemed odd. Anyway, yeah, start here and just use your parentheses and work that out, and you'll be fine. Okay, 7. I believe we just have one more left. Please just be... Oh, good. Almost done. All right. In a reaction, 25 grams of aluminum chloride was mixed with 30 grams sulfuric acid, producing aluminum sulfate and hydrochloric acid. Upon completion, 28.46 grams of pure aluminum sulfate was isolated. Calculate the percent yield. Okay, well, in order to calculate the percent yield, if I measure 28.46 grams of aluminum sulfate, I need to know how many grams of aluminum sulfate will result from mixing aluminum chloride and sulfuric acid. In order to know how many grams of aluminum sulfate will result from mixing aluminum chloride with sulfuric acid, I need to find out what the limiting reagent is between aluminum chloride and sulfuric acid. And in order to find out what the limiting reagent is between aluminum chloride and sulfuric acid, I need to have a balanced equation. So let's start there. Aluminum chloride. Aluminum has a charge of 3. Chlorine has a charge of -1, so that's AlCl3. With 30 grams of sulfuric acid, as you know, Johnny was a chemist, but Johnny is no more because what he thought was H2O was H2SO4. And that yields aluminum sulfate. Sulfate, you'd think I would know this by now, has a charge of -2. Of course, I know that. I should have known that just by looking at that. For heaven's sakes. So, -2. So, aluminum has a charge of 3, so this will be Al2SO43. And hydrochloric acid. Hydrochloric acid, that's easy. That's just HCl. All right. Now, is it balanced? Of course not. But you can see here, I'm going to start with my aluminums. I have 2 aluminums here, but only 1 here. Let me put a 2 right there. Looks at my phosphates. I have 3 phosphates here and only 1 phosphate here, so I put a 3 right there. And let's see then. Oh dear me, no. Okay, and now I have 6 chlorines. Oh, but look, I have 6 hydrogens. Splendid. 6 HCl. Okay, so next step, that was balanced equation. Next step, what's my limiting reagent? So I'm going to start with the aluminum chloride. So 25.00 grams of aluminum chloride, AlCl3. Convert that to moles. 1 mole AlCl3. What is the atomic mass of aluminum chloride? Aluminum is 26.98. And chlorine is 35.45. Of course, I have 3 of those. Add that together. 133.33. 133.33 grams AlCl3. I'm going to compare that to sulfuric acid. So this tells me that 2 moles of AlCl3 is equivalent to 3 moles of H2SO4. And finally, convert that back to grams. So that's going to be 1 mole H2SO4. What is the atomic mass of sulfuric acid? I do not know, but I know that sulfur here is 32.07. Hydrogen is 1.01 times 2, that's 2.02. Add those two together. And SO4, I already did the sulfur, I need 4 oxygens, that's 64. 98.09. And that is grams of H2SO4. So let's calculate that. So 2,533.33 divide 3 times 2 divide 98.09 times 27.588. I have 4 sig figs, so this should be 27.59 grams H2SO4. So let's see here. I have 25 grams of aluminum chloride will require 27.59 grams of sulfuric acid. Oh, but I have 30 grams of sulfuric acid, so that means aluminum chloride is limiting. AlCl3 is limiting. All right, so now I can use this to calculate how much ammonium sulfate should be created, which I can compare to the actual experimental result to find the percent yield. So starting here, 25.00 grams of aluminum chloride, 1 mole of aluminum chloride, 133.33 grams of aluminum chloride times 2 moles of aluminum chloride. All right, so now I want to go to aluminum sulfate. So that is 1 mole of Al2SO43. And finally, convert that to grams. So 1 mole of Al2SO43. What is the atomic mass of aluminum sulfate? I don't know, but aluminum is 26.98. I have 2 of those times. Sulfur is 32.07. 32.07. I have 3 of those times. I have 12 oxygens. 12 times, oh, let me add these 2 first. There we go. 12 times 16, I think is 144. No, 192. Good thing I checked. Yeah, because 12 times 144, you knew that. Come on. Okay, plus 342.17. 342.17 grams Al2SO43. All right, do this math. 25, enter. 133.33 divide 2 divide 342.17 times. That comes out to 32.07. I should have 4 sig figs. So that's 32.079. That will come out to 32.08 grams of aluminum sulfate. Okay, so that's how much aluminum sulfate will result using this reaction and accounting for the limiting reactant of 25 grams of aluminum chloride. So it's asking for the percent yield. I know that this much was actually found. So again, percent yield is equal to my actual amount, which is 28.46 grams, divided by the theoretical amount, which is what stoichiometry gives you, 32.08 grams, and multiply that by 100. So 28.46, enter, 32.08, divide 100 times, that is 88.72, which is a pretty good yield, 88.72. Yeah, not too bad. Not too bad. All right, good. Whew. That was a yeoman effort, but obviously, you know, you guys have had this for almost 2 weeks now, so you probably just did a little bit here and there and managed it quite easily, I'm sure. But there it is. Okay, excellent. Thank you very much.